This is the exact 3D model of jet engine you'd see in actual airplanes, fighter jet, or even military drone. But can you actually build a real, working, thrust-producing version of this out of solid metals right at home? Well, building one of these has been my absolute dream ever since I was just a fast swimming sail, all the way to now being a crazy engineer. But making this happen is a total nightmare of a challenge. I'm talking micron level precision, perfect balance of parts, and finding an alloy that won't literally explode at 120,000 RPM in over 800 degrees, bearings that won't melt under that crazy heat, and doing all of this in my tiny workshop. You might think it works in a very complicated way, but it's just the 3 simple steps: compression, combustion, and the exhaust. Imagine by spinning this compressor wheel, I can collect this much of air. Then I heat this air from 25 to about 800 degrees. Basic physics says that when temperature goes up, air molecules push apart and move crazy fast. So instead of that small amount, we get this much air. As the air escapes, it spins turbine. And because these two wheels are connected by a single shaft, it forces the first wheel to spin too, creating a loop and generating thrust. First, I decide to build the compressor stage. This section itself is made of 3 parts: the compressor wheel, diffuser, and outer cage. For the diffuser, aluminum works perfectly. The temperature in this section won't go over 180 degrees Celsius, and since aluminum can handle up to 600 degrees, it's more than enough. So I cut a perfect aluminum score using my Micra CNC. Next, I placed the 3D model in the center of the aluminum score and send the file to the CNC. You probably think the center would be my 0, coordinate, but not for this project. To get high precision, I used the XYZ probe on the corner to find the exact coordinates. The number I saw wasn't 0, and it gives me the perfect accuracy needed for a jet engine. Anyway, I started with the big bits to clear out the bulk, and then moved on to tiny bits for the details like drilling screw holes, making channel for the fuel and oil lines, and carving out those diffuser wings to guide the air straight into the engine. After finishing the front side of the diffuser, I flip it over and repeat the exact same steps for the back. The final result, absolutely amazing. Perfectus. Next one is compressor wheel. Because it's at the air intake and doesn't connect to the fire chamber, I decide to use a resin 3D printer. And that means lighter weight and extreme precision. Exactly what I'm looking for. But to make it stronger, I sliced the model and made the back plate from an aluminum sheet. Also used the exact same resin printer for the diffuser casing, but this time with a clear resin. The compression stage is done, but you might be thinking, why not just use a simple propeller instead of all of this trouble? Well, the reason is simple. We don't just need a fast air, we need a high velocity, high pressure air. You can actually see the exact same setup in a car turbochargers and even vacuum cleaners. The compressor wheel, a diffuser, and a ton of high pressure air. Next up is the combustion chamber. In this stage, I have to use the absolute minimum amount of space to increase the temperature as much as possible, somewhere around 800 degrees. Well, aluminum won't cut it anymore, so I switch it to steel sheet. I finished the CAD design for this part and send it out for the laser cutting. As for welding, I'll just say this. I'm an electrical engineer trying to weld for very first time. Not too bad for first time. The only thing is left for this section is the fuel lines. I used the copper tube for this, bent it into a circle and drilled 2mm holes all around it. Then fit the thinner tubes inside, welded the copper, and that's it. The only important trick here is to place this tube exactly in the middle of circle so that all the flames burn perfectly evenly. The next section was the connection between the compressor wheel and the turbine wheel, meaning the shaft housing, shaft itself, and bearings. You might think that since the housing sits right inside the combustion chamber, it needs to be made of something that can handle up 800 degrees. But the reality is aluminum works perfectly here. That's because this section is constantly being cooled down by the incoming air from the compressor. And luckily my CNC, the Makera, has a force axis to machine this aluminum cylinder. I locked it tightly onto the machine and start cutting. But to make the final result look beautiful and precise, I used an engraving bit to clean it up and give a polished finish. My main challenge after this was putting the bearing right in the center of the cylinder, with absolutely zero room for error. So here's the solution. First, I designed a circle that exactly matches the cylinder's diameter, machined it into an aluminum block and fit the pieces inside. Then, using that exact same center point, I drew a second cylinder matching the bearing's diameter. Only this time I machined it just a bit higher up. To build a shaft for this jet engine, everything has to be accurate down to hundreds of a millimeter. The slightest mistake and the whole project, boom, blows up. But did you know the exact same things happens with our personal data online? All of our information, from our full names and emails to our home addresses and phone numbers, is floating around the web, collected and sold by data brokers. Scammers then use this exact data to build a hyper-realistic phishing image and text, open credit accounting your name, or even track down where you live and harass you. That's where today's sponsored Incogni comes in. Go to incogni.com/skillmake to take back your privacy. Incogni automatically requests data brokers to legally erase your personal information from their databases. On their dashboard, you can track requests and erase data in real time. With their unlimited plan, the exposure scanner pinpoints everywhere your leaked data is hiding online, so human specialists can handle the removal. Plus, you get a personalized risk assessment every 30 days to track your privacy progress. To erase your digital footprint, use code SKILLMAKE at incogni.com/skillmake for 60% off, or click the link in the description below. Now let's back to the project. Now the shaft itself. Since it sits inside the housing, it won't get too hot, but it does spin at a crazy high speed. That's why I used MO40 steel alloy, the exact same materials used for a car's drive shaft. The only important thing here is to machine it in one single setup. Once it's clamped on the lathe, I can take it out until the final shape is done, ensuring it stays perfectly balanced. The next challenge was the jet engine bearings on the both sides. Standard steel ball bearings just wouldn't cut it. As the temperature went up, they expand and lock the whole thing up. Fortunately, I found ceramic ball bearings. Since the balls are made of ceramic, they can handle the heat much better, solving the biggest problem. So I installed one on each side of the jet engine along with the shaft. Also, to keep the bearings lubricated while the jet engine was running, I drilled 2 holes in the bearing housing and rotated a pair of copper tubes right next to the bearings to fill them with oil. The next and one of the most important part of the jet engine, it sits in the hottest zone of the engine, and its main purpose is to supercharge the gas speed from the combustion chamber and direct it perfectly. This is the NGV, or nozzle guide vanes. Well, I'm breaking this build into 3 steps: the inner ring, outer ring, and vanes. For the rings, I decided to go with the steel because it can handle up to 1100 degrees. So we started machining them to the exact size. And finally, the wings. I laser cut them from a sheet of steel, but since they also need a specific curve, I machined the negative shape of the wings into an aluminum block to stamp them. Also, I have to give a huge shout out to Makera for this CNC. I'm using the Carra Air here, and it's been such a solid and reliable machine for my workshop. If you want to grab one yourself, check out the link in the description below. The next challenge was welding these wings at the exact right angle to the rings. So for this part, I 3D printed a jig with the negative shapes built into it, locked everything in place and start welding. For the jet engine casing, I decided to go with quartz glass flanked by aluminum on both sides. This glass can handle temperature up to 1000 degrees Celsius, but it's still pretty risky and I don't recommend it at all. I only did this for the video and I'm definitely not going to push it too hard. And finally, after 50 days from design to fabrication, everything is complete. The only thing is left is turbine wheel. Now you might think I just used the steel like I did for the NGV to handle the high heat. But this turbine spins at mind-blowing RPMs. It's not a stationary part. The only thing actually works here is Inconel, an alloy engineered especially for this exact job. I really wanted to make it myself, but since it's made through metal casting, buying it just made more sense. You can easily find it on AliExpress, and the best part is that it comes fully balanced. Finally, the first jet engine test. But before that, first came the bearing lubrication. I used the spray grease for that, and for the fuel, I went with camping gas, which is a propane-butane blend. The first test didn't go well at all. The turbine wheel was rubbing against the housing, but I fixed it by adjusting the bullets. I also added a spark plug to the engine this time, so I wouldn't have to light it manually, and switched the engine oil for the lubrication. It felt like it was right on the brink of coming to life. So for this run, I hooked up a high-powered blower and cranked up the gas pressure a bit. and finally it fired up. But don't forget to subscribe, because in the upcoming videos I'm going to improve it and run it trustless on it. See you in the next video, and bye bye.